on graphs of exponential functions. So you should have completed lesson 3-2 on what an exponential function is. Make sure you kind of understand that. Maybe go back and look at some of those examples. And then in 3-3 we did some applications, so you were able to use some of those equations to solve some more realistic problems. Now, these are the types of graphs you should have. It should look like this kind of curve shape. These ones on the bottom are exponential growth because as we move to the right, they're getting bigger and bigger and bigger. And the two on the top are exponential decay because they're getting smaller and smaller and smaller. You should notice some similarities and some differences on this page. The first thing to note is that they all cross the y-axis at the same place, at 1, at the point 0, 1. So that is an interesting fact. As long as the equation is something to the x power with no other adding, subtracting, multiplying, shifting, stretching kind of things, then it will go through the point 0, 1. And then depending on what this base is, it will either decay or grow. If it's a fraction, like 1/2, something smaller than 1, then it's going to shrink. So if you multiply by 1/2, you get smaller and smaller and smaller. If you multiply by 8/9, you get smaller and smaller and smaller. So if this b number is less than 1, but still a positive number, you will shrink. If this b number is a big number, bigger than 1, like 2, you will double. So this graph right here is actually doubling. Every 1, it's just a different scale. Every 1 I go over, it goes up twice as far. So instead of being at 1, now I'm at 2. When I go over to 2, it's up at 4. When I go over at 3, it's up at 8. It's kind of hard to tell where you are on the graph, but that is, this one is specifically y equals 2 to the x, which is labeled on here. These graphs aren't in your notes. This was just to kind of give you an overview of what they look like. And now we're going to explore them a little bit further. So first of all, the base, that b that I was talking about, y equals b to the x, the base determines whether it is increasing or decreasing. So I can look at an equation like this and know right away if it's increasing or decreasing. And I talked a little bit about that on the last page. How do we know if it is increasing or decreasing? Well, it depends on what this b number is. So let's talk about what b is allowed to be or is not allowed to be. So obviously it can be 2 because that was one of the answers, but it's easier to talk about what it can't be. So I asked my class this today and they figured out pretty quickly that b cannot be negative. What happens if I take a negative number to the first power and then to the second power and then to the third power, and let's do one more just to see what happens to the fourth power? Well, I would get -2, and then I would get +4, and then I would get -8, and then I would get +16. Well, if I try to graph that, I'm going to get -2 and then +4 and then -8 and then +16, and I'm getting this crazy bouncing back and forth happening. So b, the base, cannot be negative. You can have a negative in the front, and we'll deal with that later when we do shifts and stretch and things. What else can it not be? Well, probably don't want any imaginary numbers in there because it's pretty hard to graph an imaginary number. So we want to keep it real. So that b number needs to be a real number that you can actually find the value of. It still could be a weird number like the square root of 2. That can be a base. That's a real number. We cannot have the square root of -2 because that's an imaginary number. All right, there's a couple other things that are important. Oh, the opposite of negative is positive. I should have listed that as well. So basically, b has to be positive real number, okay? There are, however, a couple of specific numbers that it also cannot be. So think about your numbers and the properties of numbers, and these are supposed to be growing or decaying exponentially. So what happens if b is 0? Then I get 0 to any power. What's 0 to any power? Well, it's 0 because it's 0 times 0 times 0, and so it's 0, which is not growth or decay. That's a flat line at 0. Not very exciting. Also, another number that kind of behaves the same way is 1. You take 1 to any power, you just get 1. So you get a flat line. But these aren't considered exponential because you don't get a curve. You get a flat line, which is linear. All right, next up, when you look at a graph of an increasing function, that would be, there is a typo on this page, so we are going to fix that typo once my computer starts working again. There we go. Nope, it's decided not to let my pencil work. Uh-oh. I'm not going to be able to write on this, and we're going to have some problems. There we go. All right, so if you have a graph that is increasing, the b value must be greater than 1, not greater than 0, because if you have a fraction like 1/2, that's decreasing. That's in between 0 and 1. So all the little decimals between 0 and 1, those are going to make a decreasing graph. And anything bigger than 1 is going to make an increasing graph. That's really it. If it's going uphill, it's bigger than 1. Even if it's 1.1, it's just going up slower. All right, now we're going to fill in some more blanks. The value of the base also gives you 2 points on the exponential function, well, f of x equals b to the x, or y equals b to the x. So if you know what the base is, you can find 2 values. One of them I already mentioned earlier. The easiest one is the y-intercept. If you plug a 0 into the x, you get any number, positive real number, to the 0 power will equal 0, or 1. Sorry, anything to 0 power is not 0, it is 1. So when I plug a 0 in for x, I got a 1 out for my answer, and that's the point. As long as you have a really simple exponential with not much going on here, it's going to go through 0, 1. Next up, I like to always plug in 1. So if I have base to the 1 power, I'm always going to get whatever that base is. So when I plug in a 1, I always get out whatever b is. So 1b will be the next point on your graph. I'm trying to get a different color dot, but it's not going. There we go. So 1, 2 is the next point on my graph. If I wanted to find more, I could plug in more, but then b squared, I don't know what b squared is, so 2 would be b squared and so on. And last of all, does anybody remember what this x-axis, what this is called in relation to this graph? It comes on down, but gets closer and closer and closer and never touches it. So that is called a horizontal, in this case, asymptote. So we have a horizontal asymptote, which is the x-axis, or the line y equals 0, same thing. Okay, so we are looking at graphs. We probably want to talk about domain and range. So in this equation, f of x equals b to the x, what values of x can I put in? You can also look at the graph. Where am I on the x-axis? Everywhere. I'm going this way forever, and I'm going this way forever. It does look like it goes up. It does go up, but it also goes over. So can I plug in a, what's off the graph here? 5. Can I plug a 5 in here and get an answer? Yes. Can I plug a 100 in here and get an answer? Yes, it's going to be gigantic, but yes. So that means the domain is all real numbers. So we write that right here, all real numbers. And the range is not up and down forever because we never go past 0, right? So, and we also never even touch. So the range is just above 0. Make sure you do not put an equal to here because it doesn't actually touch. Even though your pencil might look like it touches, it does not. Your numbers are going 1/2, 1/4, 1/8, 1/16, 1/32, and just getting closer and closer and closer, but not quite getting there. So that is an asymptote. So the domain and range of these, actually, if you look at all these graphs, they all have the same domain and range because they go left and right forever, and they're all going right down and not quite touching 0 there. So how do you tell what the graph is? Well, they all go through 0, 1, so we already know there's no multiplier or anything weird about them. It's just going to be y equals something to the x. So you just go over to 1 and try to make a straight line and figure out which number it goes to, and that is going to be your power. So 4 to the x, because I plugged in 1 and got a 4. This one's a little harder to tell, so if you went absolutely straight up, where do you hit? I'm not actually sure because those are so close together. So if they ask you this like on apex or something, they probably would label the point. They have a 9 here. It's really hard to tell. That's okay. If it's shrinking, it's hard to guess this one because it's in between, but we can go to the left instead. If we go left 1 and up, we're definitely at 2. So that means because we went left 1 and up 2, then if we go right 1, we're down a half. So the answer to this one is 1/2. And this one, it looks like it's less than a half, and this way is more, probably a fourth maybe. Yep, 1/4. So on the left side, you go -1/4. So on the right side, this is at 1/4. It is hard to tell. So if it's something like this without numbers, you just have to do the best you can visually. Is having a problem. Okay, so these are in your notes. I think that last set was not again. But this one is the top left on your note. What is the difference between the blue and the green? Well, one of the places my eyes go straight to whenever I see one of these things is the y-intercept. This one goes through 0, 1, and that is my 2 to the x graph, but this one doesn't. So how did it move? What happened? Well, what does this 3 in the front do? It's just like we learned in the fall, whenever you multiply a function by something, that is a vertical stretch of 3 in this case. So you're going to take your point that you had, 0, 1, and you're going to take the y-coordinate times 3, and now it's 0, 3. My original graph was at 1, 2, because when you plug a 1 in here, you get 2 out. So my new point, I will take that y-coordinate times 3, will be at 1, 6. So it's 3 times higher. Doesn't change my x-coordinate, just changes my output by times 3. All right, that's what a vertical stretch does. The domain and range don't change because left and right, it's everywhere. Up and down, it is only above 0. Anything else we need to talk about? All right, let's look at some more pictures. This one, they are different asymptotes. We'll get to that in a minute, but let's talk about the differences here. So big difference is the horizontal asymptote. So this 2 to the x is our base parent function. And then notice what changed here. It has a +5 on the end. So remember, if you just add 5 on the end of something, you move it up. So that's going to take our horizontal asymptote that was at y = 0, and it's going to move it right up to y = 5. So now my range has changed because it doesn't go down to 0 anymore. It just goes down to 5, but doesn't quite touch it. Domain is still all real numbers. I can put any number I want in for x, but the only numbers I will get out are going to be bigger than 5. Same thing for this other one, except we are going down 3. So my range is just above -3. I'm still staying above this line, y = -3, but I'm not touching it, so I'm bigger than it. And just notice that the plus and minus were tagged on to the end of those equations. So how do you move it left and right? Well, you have to put the plus or minus up inside the exponent with the x. So if you recall from like quadratics and things, you have to put it in parentheses inside with the x. Well, the parentheses aren't required here, unless you're typing it in your calculator, then they are. But because they're up in the exponent, they are stuck together. So when you put a +6 in here, which way does it move it? The opposite of what you think, it moves it to the left 6. And then when you put a minus, it moves it to the right. So the one with the -1 moves to the right, and the one with the plus moves to the left. So make sure you get that difference there. Now let's talk about domain range. The domain, all of these graphs go left and right forever, so they're all real numbers. And what about the range? Did my range change? Well, all of them are coming right down to y = 0. So because I moved it sideways, it's not going to change my up and down range answer. And my sideways domain answer was already everything, all real numbers. So if I move sideways from everything, I still have everything. All right, here is another one. These ones are, what's different about them is their y-intercepts. So they are vertical stretch of 4 and vertical compress. Because this number is less than 1, it's going to multiply it by 1/3, which is going to make it smaller instead of bigger. Notice the domain is still all real numbers and the range is still above 0, so those did not change. All right, here's one where notice they all go through 0, 1, so that did not change, but they still change shape a bit. And this time the number is up here in the exponent, so this is 2 to the 1/5 x, and that is going to horizontally stretch it. I think of it as times 5 sideways, but it's also like 1/5 of a unit upwards, kind of, sort of. Anyway, we're probably not going to have you compute those from points or anything, but a really wide one is going to have a fractional exponent, and a really, really steep one is going to have a big number exponent. So think about this. If you take 2 to a power, but instead you take it to 2 to 8 times that power, you're going to go up fast. So that's what's happening here. You're going to go up really, really fast. Now, if x is 0, you're still going to get 2 to the 0 power, which is 1. So that's why they still all go through 0, 1. But this one goes up super fast because it's 8 times horizontally compressed. If I had hands, I would squish my hands towards this y-axis. And for the red one, I'm pulling it sideways. And what about domain and range? All right, well, domain, guess what? It's going forever left and right. Even that blue one, it's going forever left and right. I could plug a 10 into the blue equation mathematically and get an answer. It's going to be 2 to the 80th, which is huge, but I would still get an answer. So domain is all real numbers, and they all are coming on down to 0 again, so they're all greater than 0 for the range. All right, so that gets us through those graphs. Oh, wait, maybe there's 2 more. Oh, this one is not in your notes, I don't think. So we have a couple more examples, but they're not in your notes. So if you want to just listen, that's fine, or if you want to write these down. So we are going to start with the parent function 2 to the x, and this time I want you to write the equation that is shifted down 5 and 3 left, and we'll also graph it. So let me start with my horizontal asymptote is at y equals 0 currently, and I'm going to move it down 5 and 3 left, which doesn't really change things. It's down here at -5, right? That's where my new asymptote is. Let's take a couple points. Here's a point. We're going to move down 5, 1, 2, 3, 4, 5, and left 3, 1, 2, 3. So this point has now moved. And another point on my graph, because this was 2 to the x, is 1, 2. So instead of 1, 2, I'm going to move down 5 and left 3. So now I am at -2, -3. That's down 5. 2 minus 5 is -3. And left 3 is 1 minus 3 is -2. So there's my new point. Now, that's enough to draw the graph. You just need to go start over here on the left along your line, and then when you get to those points, just shoot up. I don't know where it's going to cross the y-axis, but I'm not really worried about that right now. Just want to make sure you draw your asymptote, because that's going to help you draw better pictures, and then get like those 2 points. All right, what is this equation then? So I have a new graph. What is it? Well, it's f of x, or y equals, it's not 2 to the x anymore, but it is 2 to something. But what did I do to it? I moved it down 5. Well, down 5 means on the end I'm going to subtract 5. And 3 left. So up here, how do you move left? Left is plus 3. So if you plug in a 0 in here, you'd have 2 to the 3rd minus 5. So you could figure out where your y-intercept is. If you plug in a -3 in here, then you're going to get to the 0, which is 1 minus 5, which is -4. So you're going to get this point. So you can plug these numbers in if you want. Anyway, just to make sure they're right. You could also use your calculator and graph this to make sure it looks right. But that is it. So now on my new graph down here, what's my domain? Domain's always all real numbers. And then my range, because I shifted it down, is now above -5. And we already graphed it, so there we go. Let's try one more of those, or maybe 2, we'll see, and see how you're doing on it. All right, so this one, we are going to vertically stretch it by 6. Let's try writing the function first this time. So if we vertically stretch it by 6, we have 6 times 2 to the x. Make sure you note that it's not 12 to the x. It is 6 times 2 to the x, only the 2's to the x. And then if you want to flip it over the y-axis, well, flips are negatives, but where does that negative go if you're flipping over the y? It goes up here. So we actually have 6 times 2 to the negative x as our function. So let's do it now. We're in vertically stretched by 6 means we're going to do 6 times further. So it's going to go through 6. And 2 is going to go through 12. Let me explain that. So 0, 1 was my original point. 0, 1, if I vertically stretch it by 6, I multiply the y-coordinate by 6, so I get 0, 6. This point right here is the point 1, 2. If I multiply the y-coordinate by 6, I get 12. 2 times 6 is 12. So those 2 points are now points, but I also need to flip it over the y. So if I flip it over, this one doesn't change, but this one's going to be over here instead. So instead of it going uphill, it's now going to go downhill. Whoa, my graph is not going to be beautiful because those are the only 2 points I have. Woo! It's going out here towards 0. Because it's a vertical stretch of 6, all of these points are 6 times higher, so it's a little bit higher up off the graph, but it does go down. I should have gotten it a little closer there. 6 times a tiny bit, still a tiny bit. All right, that's what the graph should look like. Domain, it still goes left and right. It doesn't matter if it's growing or decaying, it still goes left and right, so it's all real numbers. This one is staying above 0. If you flip over the x-axis, then it flips upside down and it would be down here. Then that would change the range to be below. Ooh, that looks like an equal sign. We do not want that underline there. So it would be less than 0 instead of greater than. Maybe the next one has one of those. Nope, they're just all moved around. Okay, let's see. These are the answers to the last 2 problems. Oh, yeah, that one and that one. Okay. Now we're going to actually flip to the back of your worksheet and then we'll come back. So flip it over and we'll come back to those last couple examples. So let's talk about when you have just b to the x versus when you have a times b to the x. So let's just look at b to the x. We know it's a curved shape, either increasing or decreasing. It increases when b is greater than 1. It decreases when b is in between 0 and 1, like a fraction or decimal between 0 and 1. The y-intercept is always 0, 1 because we haven't multiplied it by anything. The other point, if I plug a 1 in here for x, I get b. The horizontal asymptote is called the x-axis, but we also name it y equals 0 because that is a horizontal line through 0. The domain is all real numbers. And the range is all positive numbers. So y is greater than 0, unless we multiply it by something negative. So we're going to do, if we multiply it over here, it's still a curved shape. It doesn't really have a name. It's just an exponential growth curve. It still increases if b is greater than 1 and decreases if b is between 0 and 1. My starting point, my y-intercept, is now a because when I plug in a 0, this part is 1, and 1 times a is a. So whatever this number is will be my y-intercept. And then to find the next point over, I would plug in a 1, so I would get b times a, or ab. The horizontal asymptote is the same, y equals 0, or the x-axis. The domain is the same, all real numbers. And the range is all positive numbers because we have not shifted it up or down. If a is negative, less than 0, then it would be all negative numbers. Y is less than 0, but that's only if a is a negative answer. All right, let's move to those 3 examples on the bottom. of page 12 of your notes, and all we need to write down is the transformations that happened. So what does this negative sign in the front do? Well, since it's in the front of the function, it's going to flip or reflect over the x-axis. The 3 is going to be a vertical stretch, because we're multiplying it, of 3. And what does this plus 4 on the end do? Up 4. Now these pretty much need to happen in order. These two don't really matter because they're both the same, but order of operations, we would multiply first and then add, right? So we need to stretch it first and then move it up, because if you move it up and then stretch it, it doesn't quite work the same. All right, so this one has 2 transformations. See if you can name them, and then I'll write them down. So the 0.5 makes this a vertical compression of 0.5. So make sure you got that, because this is less than 1. We're actually multiplying it by half, so we're shrinking it. And then the -7 is down 7. And go ahead and try part C as well. This one has 3 parts. Your parent function is the thing with the x on it. So this is not a part of your answer. Your answer is only the things happening to it, which are these 3 items. So the negative is, because it's in the front, not up here with the x, it's out here in the front, it's a reflect or flip over x. The 3 is a vertical stretch because that's bigger than 1. And the +1 on the end is up 1. So we didn't have any with a horizontal because nothing happened to my x's. All right, that brings us to the end of the lesson. So there is a checkup for this and then a quiz on a